Hey everyone, and welcome to this explainer. Today we're taking on a bit of a beast of a topic, but we're going to make it incredibly intuitive. We're demystifying compiler design. I want you to imagine stepping onto a massive, highly efficient factory assembly line. But, instead of bolting together cars, we're building software. So for all you computer science undergrads out there, grab your notes because we are going to break down this pipeline step by step and really unpack the essential concepts you absolutely need to know.
Right, let's just jump straight into it. At its absolute core, compiler design is trying to answer one fundamental question. How on earth does a simple line of high-level C code actually turn into ones and zeros? I mean, you type in an if statement in C++, right? But your computer's hardware only understands voltages, literally just zeros and ones. Bridging that massive, massive gap? Well, that is the sole job of the compiler. And look, mastering this pipeline isn't just some abstract theory you can gloss over. Take a look at this GATE computer science syllabus, for example. Compiler design is a massive, non-negotiable benchmark for any true computer scientist. It tests your deep, fundamental understanding of how systems actually process language. You really can't just know how to code. You gotta understand exactly how your code gets digested by the machine. So here's the blueprint of our factory today. We'll start with the compiler's core mission, then walk through lexical analysis, syntax and semantics, code optimization, code generation, and finally wrap up with the symbol table manager. Let's get to it.
Starting off with Section 1, the compiler's core mission, which is translating high-level code to target code.
Every single piece of code you write has to pass sequentially through these 6 distinct stations. We call this the analysis-synthesis model. The front end of the pipeline analyzes your source code to create an intermediate representation, and then the back end synthesizes that into your target machine code. Okay, let's zoom in on that very first station on the line. Moving right along to Section 2, Phase 1, Lexical Analysis, otherwise known as the scanner and tokenizer. At this stage, the compiler basically acts as a scanner. It reads your source code strictly character by character. Its sole responsibility here is grouping those raw characters into valid tokens. And remember, a token is just the smallest meaningful unit of source code. Now, it completely ignores white spaces and comments. But, and here's a crucial detail for your exams, the lexical analyzer does not check for structural errors. Forgot a semicolon? The lexical analyzer honestly doesn't care at all. It just happily groups the valid characters and passes the buck right down the line. Let's see this actually in action. If we feed our running example line of code, total equals count plus rate times 10, into this station, it gets chopped up into exactly 7 distinct tokens. Notice how it sorts them out. Total, count, and rate are tagged as identifiers, the equals, plus, and multiply signs are your operators, and 10 is tagged as a constant. So boom, 7 pieces, perfectly categorized and ready for the next phase. Which brings us to Section 3, Phase 2, Syntax and Semantics. This is all about checking structure versus checking meaning. All right, so here is where we finally catch those errors. Syntax analysis checks the physical structure by building what's called a parse tree. It strictly enforces the grammar rules. So yes, this is exactly where your missing semicolon triggers an error. Semantic analysis, on the other hand, checks the logical meaning. For example, the syntax of A equals B times C might look totally valid structurally, but what if B is a float and C is a string? Well, the semantic phase is going to throw a massive type mismatch error because mathematically, that just makes absolutely zero logical sense. And this brilliantly illustrates why those foundational courses you take actually matter. Under the hood, these phases are powered by rigorous mathematical engines straight out of the theory of computation. Lexical analysis relies purely on regular expressions and finite automata. Meanwhile, syntax analysis requires the much heavier lifting of context-free grammars and push-down automata to build those parse trees. This overlap is exactly why these subjects are so heavily linked in your undergrad syllabus. They are literally 2 sides of the same coin. All right, Section 4 now, Phase 3, Code Optimization. We're looking at intermediate code and maximum efficiency. Now that the code is structurally and logically verified, that massive parse tree we built gets flattened into an intermediate representation, specifically something called 3-address code. Now, this is a very strict, standardized format acting as a bridge. It literally limits every single instruction to a maximum of 3 variables, or addresses, so it takes your complex, deeply nested lines of C code and essentially breaks them down into flat, sequential, temporary steps that are way, way easier for the computer to actually manipulate.
Next, the optimizer steps in, and this is where the magic really happens. The optimizer scans that intermediate code and applies techniques like loop unrolling or dead code elimination. Just think about it for a second. If you optimize a single unnecessary variable assignment inside a loop, and let's say that loop runs 1,000 times, you literally just saved the CPU 1,000 redundant executions. It shrinks the memory footprint and just massively speeds up execution times, all without changing a single thing about what the program actually outputs. It's so cool. Let's move to Section 5, Phase 4, Code Generation, where we are crafting the assembly. We've reached the end of the physical assembly line. Here, the code generator translates our abstracted operations into raw target assembly instructions. It allocates specific CPU registers like R1 and R2, it loads up the variables, performs that multiplication and addition directly in the processor's actual hardware, and then stores the final result right back into memory. This target assembly is the final product. It's what ultimately becomes your executable machine code. And finally, Section 6, the symbol table manager, or as I like to call it, the factory's supervisor. But wait, hold on. How does the compiler actually remember that ID3 in the final assembly code was really the rate variable way back from step 1? Well, that brings us to the symbol table. Think of it as the factory manager. It isn't a station on the assembly line itself. Rather, it's a highly specialized data structure sitting above the pipeline, constantly interacting with every single phase. From the initial lexical scanning all the way to code generation, it uses advanced pointer concepts to track variable scopes, memory allocation, and data types. This manager utilizes some very specific operations. When the lexical analyzer first sees a new variable, it uses the insert operation to log it in the table. Then later, when the semantic analyzer needs to check if that variable is an integer or a float, it elegantly uses the lookup function. This continuous fetching and validating guarantees that a variable maintains its exact same identity throughout the entire compilation journey, right up until the free operation releases the memory at the very end. Grasping this sequential pipeline does so much more than just help you ace your undergrad exams. By knowing exactly how the compiler analyzes and optimizes your code under the hood, you inherently become a vastly more efficient programmer. You finally learn how to write code that works with the machine instead of against it. It's honestly a total game changer. Which leaves us with a really fascinating thought to end on today. Compilers are already incredibly sophisticated at restructuring human input into highly optimized machine hardware instructions, right? But as these analytical models become even smarter, capable of catching way deeper logical flaws and performing even more extreme optimizations, how is that going to reshape the way we write code in the future? Like, are we even going to need to worry about syntax at all? Thank you so much for joining me in this explainer. Keep studying, keep questioning everything, and I'll see you in the next one.